Good evening, everyone. It's Smitty Halibut here. Doing my next Smitty working on something. I haven't done one of these in a while, but we just got back from DefCon a couple of weeks ago, and we had a very successful DefCon DarkNet project. Go check it out at http dcdark.net. That URL will be down in the comments below. But one of the things, we got a lot of positive feedback, good and bad, and things to do better and whatnot for next year. And one of the pieces of feedback that we got a lot of is that we need to make some changes to the way the DarkNet badge was designed. This year's badge was pretty complex. Padre and Cranky Hippo just tried to assemble one of these on an episode of Know How. Let's see if I can do this without too much glare. But they're kind of two boards. It's a kind of a complicated stack of a bunch of stuff going on. There's a STM32 microcontroller board in there, an infrared transmitter and receiver, just a green LED for status. Let's see here, some power management. Then on the main front display board, there is an OLED display there, a 12 keypad for T9 text entry. And then on the back of it is a RF module. It's an RFM 69HCW, I believe, and then a bunch of surface mount LEDs with some surface mount resistors. There were a lot of things. This was a great board. When you finally got it up and running and functional, it was very powerful, and a bunch of batteries on the back. Very powerful. It could do a lot of stuff. It used the infrared for key negotiation, key transfer between badges. So if you have two of them, you could pair them up like that, and they would transfer elliptic curve public keys across each other. And you would end up with a little phone book of all of the badges of information that you, badges of whose identity you already had. And then you could go into your address book and say, I want to send this particular person a message, and it would use the radio module to do that. We got the basic platform kind of defined this year: the STM32, the RFM module, the OLED display, the T9 keyboard, the infrared transmitter and receiver, and that's kind of a generic platform. But we're going to play around with the layout of it. For example, there were an awful lot of headers in here. The headers that you use to connect the two boards together on both sides, you had to solder, both the male pins on this board and the female pins on that board, plus the 40 pins, 20 on either side here for the STM32 module. And if your module was bad or died or broke in any way, Lord help you if you need to be able to unsolder those 40 pins and put a new board on there. And there was also some weirdness because like the middle two battery terminals here are underneath the board. So you have to put the headers in first, then you put the battery terminals in, then you put the CPU board on, and and hopefully you don't have to undo those battery terminals and get them off to do any rework or anything like that. So there were a lot of complexities, let's put it that way, with this board. And if you were a good solderer, had some experience, and knew what you were doing, you could make a pretty awesome badge when you were done with it. But we need to optimize for noobs, and not said with any malice, not said in any sort of a negative way, just people who don't have a lot of experience doing soldering. So that's what I'm going to be doing. Rather than using the header-heavy STM32 modules that you can get on eBay. These are really neat modules. If you want to play with the STM32, that's a good way to do it. And they're cheap. They are dirt cheap. When you buy these in quantity, we ended up paying, I think, just over $3 a piece for these. If I go to Mouser and try and buy just the CPU, just the STM32 F103 mumble, I don't remember the rest of it, just that chip alone costs more than what we paid for this entire module, with the chip, all of the crystal oscillators, the USB connector, all of the support hardware and everything else. And so that was a really compelling reason to go with that. But that 40 pin header, those 40 pins worth of headers, is just too much. It's boring. It's repetitive. It doesn't really give you a good flavor of what it is to solder. And if you break it, or if you do it wrong, you were really screwed, because taking out that 20 pins in a row header is just nearly impossible. Trust me, I know. I had to do it. There were a couple of other little minor problems with the badge, some weird things. I think it was more a fab problem. I don't know if you can see it on the display here, but if my camera will focus, there's a little outline around that big solder pad there. It's kind of a heatsink pad for that diode. There's a little tiny outline on it. What happened is that the solder resist mask was too large for that hole. And so the rectangle of where there was not any solder mask was too large, and it ended up exposing the ground plane a little bit. And so if you put too much solder on there, it would bridge across the middle big pad that you solder that component to and to the ground plane. And unfortunately, that was not a ground pad. So shorting that out basically shorted your power to ground, and that's never good. A lot of warm batteries that weekend. So those are the kinds of things that I'm going to go in here and change. I want to stay with the same general platform, though. I want the device to be compatible when I'm done. So it's still going to be an STM32, but rather than using that module, what I'm going to do is I'm going to make a board. My intent is to make a board that that will be pre-populated by a lot of the surface mount components. I don't want to give that STM32, that little tiny, what is it, TQFP 44 or 32 or whatever it was, that little tiny chip. I'm not going to be asking people that are new to soldering to try and solder that chip on there. Similarly with the micro USB connector on there, they're just too small. We tried that in the past and it didn't work out. It was a miserable failure. So instead, what I'm going to do is I'm going to make a board that has the parts that are only available in surface mount pre-populated on them. So we're going to send them out to fab and they're going to put some of those parts on. But a lot of the parts that don't need to be surface mount, like the resistors and the capacitors and the LEDs and the crystals and the display and the buttons and all those things, we're going to keep those as through-hole components. And we're going to keep those as kit components for the Learn to Solder part of the badge. I also want to make it one big board instead of two smaller boards so that we can do away with the headers that join them in the middle. It's going to change the aesthetics of the board. And right now, honestly, I don't care about aesthetics. Right now, I just want to get a functional board, kind of a test platform that I can give to the software guys so that they can start writing some of the software. So we have some pretty basic software on here, basic functionality this year. The goal is to use the same platform and to extend the functionality so that next year when you come back with this badge, you'll be able to reprogram it, put the new flash on there, and get all of the new functionality. Also, if you get the new kit, it will be a little bit easier to assemble, but it will be compatible. It will have all of the same functionality. So that's our goal. That's what I'm going for. It does not look like anyone has joined the broadcast yet, so I'm still by myself. And yeah, that's what I'm going to be doing. I'm going to be using KiCad. Crux, the gentleman who designed this badge and the last 4 years worth of badges, he uses Eagle. I'm going to be using KiCad. It's personal preference. They both have their advantages and disadvantages. I'm more used to KiCad these days than I am to Eagle, so I tend to use it more. But I've used Eagle before. Eagle is much better at doing artwork on the board, and that's something that Crux has always been into. So kind of some spiffy fonts up at the top there. There's some, well, that's all just text, but there's some cryptographic puzzles on the back of the badge. There's a little bit of artwork at the top there. Again, my camera's not focusing very closely. But Crux has done some cool stuff. Oh, and then, of course, he's got the command code logo down there. He's the one who wrote all of the software, or most of the software, and then Crux's logo down there. So Eagle is much better at that kind of artwork than KiCad is. KiCad's kind of a pain in the butt to do that. But I'm going to be using KiCad. And again, like I said, I don't care about aesthetics. I care mostly about functionality. So that's what I'm going to be working on. So this is the KiCad schematic capture program. It's the same program I've been using for a lot of my other Smitty working on something projects. I'm using the Google Hangout screen share thing. So anytime a pop-up comes up, the pop-up itself won't be shared, unfortunately. That's just kind of a limitation of the applications. Like right now, I'm in a pop-up. The cursor just kind of stops moving around. That's how you can tell, and that's unfortunate. But I realized that the pop-up that I was just in was not was the component selection pop-up, and I don't have an STM32 defined in here. So I'm going to have to go to the library editor. So let me open that up and share that screen. Okay, so I need to select the working library. I've got my own, and it has not been added yet. The joys of setting up a new project. I've got to add my custom library. Stand by, please. Apps, KiCad, Smitty.lib. Okay. So, okay. Now I'm going to go open a library. I'm going to open the Smitty library, and I've got the Smitty library open. I am now going to create a new component. Component name, STM32F103. There's one, create components. Nope. All that looks good. Okay. All right. So start out with some basic things here. I need to start laying some pins. STM32 F103 CBT6. That's the one we were using. There's the data sheet. So let's take a look at this. Come on. All right. So here's the data sheet for the STM32. The one we're using specifically is the STM32 F103, and then I believe it's a CBT6 is the one. But it's a neat little microcontroller. It's an ARM-based, it's a 32-bit ARM Cortex. It's an ARM M3. Runs up at 72 megahertz. It's got a whole bunch of I/O. It's got a bunch of flash. The chips that we used this year were 64K of flash. We're going to go up to 128 next year. It's got 20K of RAM, which is nice. Pretty big for a microcontroller. They're definitely bigger, but all the AVRs are smaller, which is the primary reason we upgraded. We were using an AVR in past years. The the ATmega 328s. And we just ran out of RAM. Could not make it all fit. I'm not going to go into the details of the STM32. It's a neat chip. It's got an awful lot of I/O. You can see a bunch of I2C, SPIs, UARTs, timers, all kinds of fun things. It also does USB directly on the chip, which is convenient. It allows us to do some fun things with micro. And right now I'm just looking for a pinout. Nope, that's the LPQF. Blah blah blah. That is not 64. Is it the one we have a 64 pin? I don't think so. 48? 36. Which one are we doing? This is the kind of thing I should know, isn't it? 1, 2, 3, 4. That is no more. Oi. All right. I'm not going to count because I can't see and I don't have eyes. I think we're using the VQFP N36. I think that's the one we're using. If I remember correctly, there's a table in here that lists which models have which packages. Oh, shoot. Oy, oy, oy. Lots of stuff in the data sheet. You catching all of that? Read all of that. It's important. We'll get back to that. No, we're not. All right. Not QFN. I think it's QF. No. LQFP 48. No, it's pinned. Where? Come on. Maybe it is the LQFP 48. I know this is terribly exciting, isn't it? I think it is the 48. All right. So I'm going to go put this one, I'm going to go draw that one up in KiCad. I can't drag that one, can I? Whoa, oh, too fast. Okay. Oh, nope. Let's not have you guys looking at my Twitter. Okay. I'm going to unshare that one. Hi there. And I'm going to share back my component editor. Parts library. There it is. Okay. So let's start laying out some pins. Unfortunately, y'all can't see both of these at the same time. But we'll do that. Pin name, V at pin number 1. Oh, that's big. PC13, 2. Oh, this is going to be really big. Okay, PC14, pin 3. PC15, pin 4. PD0, pin 5. I'm put better descriptors on these. PD1, pin 6. But what I'm doing right now, RST, just reset, is I am creating a component. So when I'm done with this, I'm going to wrap a box around it, and this is going to become the component that I can use in the schematic capture program. In fact, I'm not even sure I want all of these oriented the way I'm doing them. VSSA, VDA 9, PA0, 10, PA1, 11, PA2, 12. Reorganize these in a way that makes more sense later. PA3, 13, PA4, 14, PA5, 15. And all I'm doing here is just copying what I see on the sheet. Magic to what I'm doing here. PA7, but then it goes to PB0, 18, PB1 on 19, PB2 on 20, PB2. PB10 on 21, PB11 on 22, VSS 1 on pin 23, and VD1 on pin 24. Okay, let's check the side. I'm going to change that to be a left, and then PB12 on pin 25. And PB13 on 26. PB14 on 27. PB15 on 28. PB15 is the last one that goes to PA8 on 29. PA10 on 30. Right. Oh, Ooh, PA9 on. And then PA10 on 31. PA11 on 32. PA12 on 33. PA13 on 34. 13, 34, yes. And you'll notice that 2 pins on every corner are these, with one exception, are the power lines. VB2 on, no, ESS2 on 35. E2 on 36. And then going up to the top, PA14, 37. PA15 on 38. PB3 on 39. PB4 on 40. These are very consecutive, are they? PB5 on 41. PB6 on 42. PB7 on 43. And then boot 0 on 44. PB8 on 45. PB9 on 46. This is terribly exciting for you. VSS 3 on 47. And VE3 on 48. And look at that. It's at the same level as the one. So I got it. All right. So I could just wrap a rectangle around this and call it a chip. And that is all of the orientation of how the pins are laid out, although the pins are laid out in a square, not in a rectangle like this, with pins on all sides. But when I'm doing things in schematic, I don't care too much about how things are laid out physically. I care much more about logical groupings. So I think I actually want to pull all of my all the pins, like all the GPIO pins out on one side, all the power pins into one area, that kind of stuff. So I think I kind of want to move these. Well, or I can just not worry about it and use tags everywhere. I think that's what I'm going to do, because I'll be honest with you, I'm kind of not in the mood for doing component creation right now. Rotate that, I'll put it down in the middle, ka-chunk, STM 32F103, perfect. I'm going to call that a component. And I'm going to, A. Crikey. I want to put pin 1 right at the origin. Okay. So, load component, nope. Update current component in current library. Create a new component from the current one. I already created a component, didn't I? The current library, import, export, update current component. There we go. All right. So already exists. Change it. Yes. Okay. So let's save the library. Yep. And it's there. So I should be able to quit out of here. Hi again. It's me. Screen share. Go back to that. And now when I go into here and lay a component down, 2. Oh, yeah, because I'm silly. So apparently I already created one. I didn't show up last time because I had not yet loaded my custom library in. So remember what I was saying earlier about collecting all of the powers together and a couple like the bat and the reset and then all of the PBs together and all the PAs together and the couple of PCs and PDs, all of them together. Well, that's what I had done on the last time. Glad I didn't go through all of that effort this time. All right. So I've got my chip. Let's see here. What else do I need to lay out? Let's go for the infrared LED. Small. And we'll rotate that point down because that's how I look at things. And let's get the infrared receiver, which is another one that I think I have created. I got two of them in here. And the difference is the pinout, and I'm not entirely sure which one we're using, so I'm just going to do that one for now. We need to drop a resistor on the LED. I don't need a resistor over there, but I do need some power. So let's load up a ground. Put that there. Copy that over to there. Oh, we haven't done power yet. Okay. Do I want to do AAAs? I'm going to, for this board, I'm going to punt on the power problem. How do I want to do this? For this board, I think I'm going to punt on the power problem and just give myself an external power input. So two pin connector, yoink, and we're gonna copy my ground up there, and we're gonna lay out a new power for VCC. Okay, now let's connect all of this up. La di da da da. And we'll copy that over here. Okay. So I now need to assign some pins. One is a transmit pin for the LED, for the infrared transmitter, and one's a receive pin for the receiver here. I'm going to punt on pin assignment for a bit, and I'm just going to tag this as RTX and RX. Okay. Tag those up. Okay. So later on, when I figure out what pins those need to go into for backward compatibility, basically I just got to look at Crux's design. I will take those same tags and put them on the right pins over here, the correct pins over here. In the meantime, that is wired up. Let's see here. What else do we need to preserve? All right, we got a button matrix. So let's go get a button. There it is. Okay. So wish there was a smaller version of that. There isn't. This is in 4 columns. The buttons are 3 columns and 4 rows. And then he added a 4th column for the LEDs. All right, so 3 columns and 4 rows. So, oops. All right. Copy block and yoink and copy block yoink. Okay, so we are going to and we're going to connect that in there, and there is our row. X0 row. Do X1. X2 and button X3. Okay. And then drag that. Yeah. So I'm not going to try and teach you how to use KiCad during this. There are a lot of keyboard shortcuts that make KiCad much more usable than if you try to do everything through the menus. For example, hovering over a component like that and then hitting M automatically puts it in move mode. For single components, you can also do a hit C and copy it. And when you're in a move mode, either from a copy or from a move, you can hit Y. Well, okay, this one's vertically symmetric, so that doesn't help. Y will flip it in the Y orientation, like across the Y axis. And I believe X will flip it in the X axis as well. And then you can hit R to rotate it around and things like that. And then just kind of what you were doing. Those are some keyboard shortcuts that I discovered that make KiCad a lot quicker to use. Okay, so those are my 3 columns of 4 rows. Let me get some up here, and I'm going to do button Y0. Y1 and button Y2. Okay. And so I don't know if you're seeing what's going on here, but we are making an XY matrix with buttons at each of the intersections. And the way it works is in software, you cycle through, let's say, rows. It doesn't really matter which way it goes because it's symmetric, but you pick one, you cycle through all the rows, and you leave most of the rows driven low, but then you take so like all of them will be driven low when you're not actually scanning, but then you take X0 and drive it high. And then the Ys are input pins at that point. So when this is driven high, you look for any lows or highs on the Ys. You know what? We're going to need pull-ups. Okay, so I was wrong. These are going to be all driven high when you're not using them, or high impedance. High impedance meaning like input lines. But then you drive one low. So let's say X0 is low. There's going to be an internal pull-up in the chip when you're reading these, so they will be internally pulled high. And then if you pull this one low, when you short that button, then Y0 is going to be driven low through that intersection. And so when I've got X0 driven low, but X1, 2, and 3 are all high, if I see a low on Y0, then I know that the intersection between Y0 and X0 has been pushed. Y1 and Y2 will still be high because they're driven high, and assuming you're not pushing the buttons. And then you scan to X1, X2, and X3 and do the same thing. And in this way, you scan through all of the buttons, and anytime you see a low, anytime you see a low on one of your inputs, then you know that the button at that intersection is being pushed. Um, that's probably not the greatest explanation for it, but trust me, it works, and it's a very efficient way of putting a whole bunch of different buttons. I mean, I got 12 buttons here, but I'm only using 7 pins rather than trying to use 12 pins for that. And I could throw for one more pin, I could get another 4 buttons over here, right? So it's you get a much better utilization of your I/O pins. The other thing that we're doing is and actually let me do that now. Um, we have a similar matrix of LEDs, and these LEDs are backlighting the board, um, and we can actually use the same X that is doing the scanning, which is kind of convenient. You have to have a different set of Y pins to drive them, because um, you're not trying to input on the LEDs. You want to you want to drive the LEDs, but you can use the same button, the same X pins, which is kind of convenient. So what I'm going to do is I'm going to do that. I'm going to copy those, and I'm going to drag them over here. Let's see here. These are going to have to be low, so I'm going to put these on the cathode side of the LEDs. Mhm. Okay, and let me hook these up. And then when it comes time to lay these out, since the LEDs and the buttons are right next to each other, um, I can actually use the same trace going across in the X direction on the keyboard to power both the buttons and the LEDs, which is kind of convenient. And okay. Then let's see here. I actually want to give myself a little bit more space here. So I'm going to move it down there. Now I need some resistors, and I've already got a resistor on the board. So let me just go up here and copy that. And I'm going to put it right there. Okay. Copy that over to there. So since we're only ever driving one LED at a time on each column, because I'm scanning across my X's, I only need one resistor here, because we're only ever driving one LED at a time. You're never going to drive a variable number of LEDs. And because when you drive a variable number of LEDs, then you need to have variable amounts of current limiting. But since we're only ever driving one LED at a time, the current limiting resistor can be constant. And it's a pretty low value, actually. I think I measured it out at one point to be like the correct value is 47 ohms. But that's because it's a 3.3 volt part, and these are roughly 2-volt diodes. So you don't have a whole lot of voltage you need to drop to limit your current. Okay, and then I'm going to LED Y0, LED Y1, LED Y2, LED Y3. Okay, and hook these up. So I got my chip. Move it out of the way. Got a little bit of power. I've got the infrared transmitter and receiver. I've got the keyboard. I've got the backlight LEDs. What else do I need down here? I need my display, and I need my radio module. Oh, that's right. We've also got the status LED. So let me add another status LED here. It's just a direct copy of this. Copy block. Edit status. Okay. So, so on this board, we've got the buttons. We've addressed those. We got the backlight LEDs. So those are actually surface mount LEDs that are facing into the board. And then I don't know if it's going to show up on the camera, but you can see little text areas on top of the buttons. And each of those text areas is what they are, is they are holes in the copper and the solder mask so that you can actually shine a light through the board. And the LEDs are immediately underneath that. And those LEDs shine through the board and backlight that text on the board. It's kind of neat. Up here around the edge, there's a DC and a DN for DefCon DarkNet. That's something that Crux has been doing since the very beginning of these boards, and it's a really neat effect. We didn't really do a whole lot with it in the software this year. Again, we kind of had a last minute, can we even get the thing working at all before we get to DefCon kind of thing. So a lot of things got pulled out of the software, but we got the basic functionality in there. I'm waving my hands at the battery and power management for the time being. I've got the status LED. I've got the transmitter and receiver. Oh, reset switch. Okay, so let's grab another one of these. Oh, let me knock that off. There. Come on. You know you want to. What's going on? Start screen share. There we go. All right, so I'm going to grab that. Hey, grab that. Put it up here. And I need a copy of that to that. I think reset is already pulled high internally, so I don't need to pull up for it. So that's all I need for the reset switch. Reset. Let me set these. IR. Yes. Value. Zero status. Okay. Value IR. X. Plus 5 volts. I'm not going to be able to punt on power. Okay, but I'm going to deal with it some other time. Oh, hey, knock that off. So I got my buttons, I got my LEDs, reset switch. So the next thing I have is the LCD. Have I already created an LCD for this? I may or may not have already created an LCD thing. I'm sorry, they're OLED. They're not LCDs. You know what? They are literally just a 4-pin header. On. Get you a 4-pin. Hey, look. OLED display. Okay. This is. Do I have pinouts labeled on here? Oh, yes, I do. Sweet. All right, so it goes ground, then power, then clock, then data. Okay, so copy that over there. Ground, and copy that one. Then power, then I2C. No, there's actually terms for this. Where did I just put my display board? There it is. SCK, SCK. Yeah. Display. OLED SCK. OLED SDA. Yeah. Okay. Pull these up. Bum, bum, and bum, ba-dum. Okay. Then the one remaining thing is the RF module. Actually, that's not the one remaining thing. We got several different things. I need to go research how to wire up that board. There's a lot of stuff that's on that board that I do not have on my schematic yet. You know, at the very least, that super out of focus shiny spot right there is the 8 megahertz crystal that it uses for the internal PLL to upscale at that to 72 megahertz for the internal clock. There's also a 32 kilohertz 768 hertz oscillator right there that lets this thing do some real-time clock work in there as well. It's low-speed oscillator. We've also got the programming headers. I need to get those on there. There's a power LED. There's the USB stuff. There's a bunch of stuff for the USB. A bunch of decoupling caps. I can go add those right now. That kind of thing. There are a lot of support pieces on that chip that I need to make sure to recreate. So I definitely got a lot of work left to do on this, but I've been going for about an hour now. Is there a time on that? I can't remember exactly what time we started, but I've been going for about an hour now, and that's probably pretty good. That gives you an idea of what it is that I'm trying to accomplish. Eventually, I will have all of the surface mount stuff pre-populated on this board, like I said, but I still want to leave the buttons and the LEDs and the resistors and capacitors and, you know, all the things that I can have through hole. In fact, I may even do like the old Type A USB connectors, the big rectangular, big square USB connector, because those are still pretty easy to get in through hole packages, and have the players solder those on. I really want to get back to, you know, just a simple board to play with stuff. So anyway, thank you very much for joining me tonight. Although it doesn't look like anyone did join me on the Hangout, but at least you're watching this now. If you've made it this far, I'm impressed. So thank you very much. Hit me up on Twitter. I am at Smitty Halibut, which is the same login as that I use here at YouTube. I suppose you can leave some comments below on YouTube as well. I don't check those quite as often as Twitter, but I will be checking those. So yeah, thank you very much. And this has been Smitty working on something. This is the DefCon DarkNet project badge for next year, 2017, DefCon 25. Just kind of doing the next iteration. Right now, just mostly recreating what was there, but I'm going to do it on a different board layout. So thank you very much for joining me, and we will catch with you next time. Be good humans. Thank you.